So today we shall be discussing about units and measurements. Units and measurements. Units and measurements. First and thereafter we will introduce what we call dimension. Now we know in physics we perform a lot of experiments to understand various physical phenomena. Experiments are the basis of physics. That is, I can say based on the results of various experiments performed, new theories, principles are formulated. Now let us try to understand the term unit or units. I know this is a term which all of us have come across from our very early science classes. But let us go a little bit deeper into unit in today's class. What is a unit? A standard reference used to represent any physical quantity is called a unit. So what I said is that standard reference. Standard reference used to measure any physical quantity is called a unit. So standard reference used to represent any physical quantity. So whenever we will be going for measurement of any physical quantity, it has to be represented by a standard reference. And that standard reference is called nothing but a unit. Now let us see what are the characteristics of a good unit. A good unit. When we will call a unit to be a very good one. Everyone wants to be good. So let us see when we can call a unit to be good. A good unit must have universal acceptability. That means if sitting here at Hailakandi I say the unit of mass is kg or SI unit of mass is kg, then everyone sitting in different parts of the globe must accept it that yes, the unit of mass is kilogram. So this is what is meant by universal acceptability. Number 2, space-time invariable. Space-time, a good unit must be space-time invariable. That means the unit should not vary with variation of space and time. If I say that today, say 15th of September 2020, I say the SI unit of mass is kg, then if I go at other countries, then also the unit of mass should be kg. That means it should not vary with space and time. This is what is called space-time invariable. A good unit should not change with change in physical conditions. Change in physical conditions. Physical condition means with a change of pressure, temperature, etc. So if there is change of pressure, change of temperature, like that, unit of any physical quantity should not change. So a good unit must have that ability. Number 4, it should be reproducible. A good unit should be reproducible. That means if I forget the unit of any physical quantity, I have to have some mechanism with the help of which I shall be able to recall the unit. I should be able to reproduce the unit. Fine. or if I know the units of very few fundamental quantities, then I should have the ability to generate the unit of any physical quantity. So that is what is meant by the term reproducible. So a good unit must be reproducible. So these are the few good characteristics of a good unit. A good unit must have these sort of properties. Let us try to understand what is called system of units. Actually, there are three different system of units. One is called CGS, another is called MKS, another system is there FPS, and the most internally accepted one, internationally accepted standard system of units, that is SI unit. Now this CGS and MKS, why I said three, these are collectively known as metric system. This FPS is known as British system of unit, British system, and this SI is internationally accepted system of units. So metric system, British system, internationally accepted system, that is SI system of units. So here CGS, C for centimeter, G for gram, S for second. Fine. Now let us try to understand what is called fundamental quantities and units. Let us try to discuss a new topic called fundamental quantities and units. The quantities which do not depend on any other quantities for their measurement are called fundamental quantities. The quantities which don't depend on other quantities for their measurement are called fundamental quantities. Fundamental in the sense that they don't depend on any other quantities for their measurement. Now what are the fundamental quantities? Let us see length. Let me explain this. Suppose I keep this pen cap in front of you and I ask you to give me the length of this pen. Now pen cap. So when I assign the task to you, what do? You just take a scale, measure the length from here to here and give me the answer. Now, for the measurement of length, you need not to depend on what is the color of the object, what is the shape of the object, what is the weight of the object, what is the volume of the object. That means you need not to depend on any other physical quantity for the measurement of length of this particular object. Therefore, we consider the length of an object to be the fundamental quantity. Similarly, if I ask you to give me the mass of this pen cap, then you need not to even know what is the length of this pen cap, what is the area, surface area of this pen cap, what is the volume, and so on and so forth. Therefore, like length, mass is also a fundamental quantity. Time is again a fundamental quantity. Luminosity, you will get it in later parts of your syllabus. Amount of substance, electric current, and temperature. These are the 7 fundamental quantities. As of now, we have length, mass, time, luminosity, amount of substance, electric current and temperature. Now all these are nothing but fundamental physical quantities actually. So definitely they will have some unit. Length will have some unit, mass will have some unit, time will have some unit. So similarly all these 7 fundamental quantities will have some units. So units of fundamental quantities are called fundamental units. So that means units of these fundamental quantities are called fundamental units. That means unit of length will be a fundamental unit, unit of mass will also be a fundamental unit. Like that, unit of all the fundamental quantities which I have named here will also be called as fundamental unit. Now, when a physical quantity is to be measured, if we are independent, we need not to depend on any particular quantity, then we have understood that that particular quantity is known as fundamental quantity. Now there are lots of quantities for measurement of which we have to depend on these fundamental quantities, and they are called derived quantities. These are called derived quantities. Now, as the name suggests, derived, that means they have been derived from the fundamental quantities. So, derived quantities are the quantities which depend on fundamental quantities. For their measurement. So derived quantities are the quantities, I can say quantities, which depend on fundamental quantities for their measurement. So definitely the units of derived quantities will be called as derived unit. Like we have defined unit of fundamental quantities to be fundamental units. So similarly we can define unit of derived quantities by derived unit. Now let us write few examples of derived quantities. There are innumerable number of derived quantities. Say I write a term velocity. All of us have been uttering this term from maybe class 6 or 7. So velocity. Now all of us know that velocity is nothing but, velocity depends on which particular quantity? Displacement and time. That means it basically depends on length and time. So it's a derived quantity. I say force, mass into acceleration. So it depends on mass, which is a fundamental quantity. Acceleration, L by t square, distance by velocity divided by time. So it depends on velocity and time. Again, time is a fundamental quantity, but velocity is a derived quantity. Velocity is a derived quantity. So velocity, force, pressure, there are lots of quantities. Huge number of quantities are there. All of them are derived quantities. Only except these 7 quantities, rest of all the physical quantities are derived quantities. And the units of the derived quantities are termed as derived units. I can write, say, acceleration. Acceleration, it is again a derived quantity. Fine. So there are, I can say, density. Mass by volume. So it depends on mass, it depends on volume. Mass is a fundamental quantity. Volume, again, it will depend on lot of other fundamental quantities depending upon the shape of the object. So density is a derived quantity. So like that we have innumerable number of derived quantities. But so far the fundamental quantities are concerned, we have only these 7. Length, mass, time, luminosity, amount of substance, electric current and temperature. Fine. Now these are very basic things. Now let us focus on to a very, very important terminology called dimension. This is very, very important for your exam purpose and also for the knowledge point of view. This is a term which perhaps you have not come across in your any previous class. So this is a completely new term that you are getting in HS first year science. And why I am telling that it is very, very important, because from now onwards, whenever you will be getting any new physical quantity, one thing has to be known to you, and that is dimension of that physical quantity. Whenever you come across any new physical quantity, you have to have the knowledge of dimension of that particular quantity. It does not mean that already the quantities which are known to you, you need not to know the dimension of that particular quantity. Of course you have to know. Fine. As of now, whichever physical quantities you have come across, velocity, speed, time, mass, weight, everything, fine. The dimension of those particular quantities also we will see how we can obtain. Additionally, I am telling from now onwards, whichever new physical quantities you will be getting, which as of now you have not got, you have to have the curiosity to know the dimension of that particular quantity too. Now, what is dimension? Dimension of a physical quantity, let me write the definition. I can say dimension of a physical quantity are the powers to which the fundamental units I can even say to which the fundamental quantity, fundamental units or quantities be raised to obtain the unit of a derived quantity. Now, dimension of a physical quantity. So first point you have to notice the dimension is related to physical quantity. If I give you a number 1, it is dimensionless. If I give you an angle, it is dimensionless. So first point is that dimension is always and always associated with a physical quantity we talk about. So dimension of any physical quantity are nothing but the powers to which the fundamental units be raised to obtain the unit of a derived quantity. Now, when I will be doing it, you will understand very nicely actually. So, in order to find the dimension of any physical quantity, or to be more precise, any derived quantity, basically what we have to do, we have to raise the power of fundamental units. Now just remember, just on the previous slide or previous page we have discussed about fundamental quantities and the units. And here also you are getting fundamental units. Now let us see how to write the dimension, how to relate the dimension of a physical quantity with fundamental units and all that. Now first of all, dimension has to be written. Dimension has to be written within third bracket. This is a rule, you can say. Dimension of any physical quantity has to be represented, has to be written within this third bracket. So from now onwards, we have to be cautious about putting third bracket while we represent any physical quantity. For example, so this is the dimensional symbol actually. For example, say length. For example, say length. Length is a fundamental quantity we know. Now how to represent the dimensional symbol of length? This arrow is just to make you understand that whatever I am writing, this will represent the dimension of length. Now what is the symbol of length? It is L. Fine? It is L. So L I have written within third bracket. So this represents the dimension of length. Now again, generally, although here it is written fundamental units, we have 7 fundamental quantity, so we will have 7 fundamental units. But generally, when you represent the dimension of any physical quantity, normally we restrict ourselves to 3 fundamental units, which are length, mass and time. Normally we restrict ourselves to these 3 fundamental units or these 3 fundamental quantities. It does not mean that we don't recognize others. We do recognize all other quantities too, but generally if we restrict ourselves to these 3 quantities and their fundamental units, our purpose gets served. So for mass, the dimensional symbol is this. For time, it is this. So you just remember, the dimensional symbol of length is this one. Dimensional symbol. These are all dimensional symbol. Dimensional symbol of length, dimensional symbol of mass, dimensional symbol of time. Now you see length, mass, time, all these 3 are fundamental quantities. And therefore, in order to represent the dimension of any derived quantity, we have to depend on these LMT, because derived quantities are the quantities which depend on fundamental quantities for their measurement. So if we wish to represent the dimension of any derived quantity, it has to be represented, it has to be expressed in terms of these symbols LMT. When I have written L, it automatically implies that the power of L is here 1, here the power of M is 1, here the power of T is 1. When I have represented the length, I can even write L to the power 1, M to the power 0, T to the power 0, because while representing length, I need not to depend on mass and time. So even I can represent like this, or even I can say M to the power 0, L to the power 0, T to the power 0. For representing the dimension of mass, I can even write M to the power 1, L to the power 0, T to the power 0. For representing the dimension of time, I can say M to the power 0, L to the power 0, T to the power 1. There is no harm. Fine? So this is what is called dimensional symbol. Now one thing you have to be extremely cautious, that numerical numbers, angles are dimensionless. That means they have got no dimension. That means M to the power 0, L to the power 0, T to the power 0. Numerical numbers, angles are dimensionless. So if I get half, what is the dimension of half? It is 0. I can say it is dimensionless, that means M to the power 0, L to the power 0, T to the power 0. Or I can say it has got no dimension. Fine. If I get angle, it is also dimensionless. Now let us just find the dimension of 2-3 quantities. Fine. Let us see the dimension of area. Let us find the dimension of area. Area of any particular thing, no problem. But area, in general, we are talking about area. So say the symbol of area is A. Symbol of area is A. So when I intend to represent the dimension of area, I have to write like this. The moment I write A within third bracket, it automatically implies that I am representing the dimension of area. So dimension of area. Now dimension of area will be what? Area, that means either it will be length square or it will be length into breadth. Now, I have explained on my second class that breadth is also basically a length. When we intend to measure the breadth, basically we measure the length between two certain sides, certain edges. So breadth is also basically length. So that means area is nothing but L square. Fine. So I can write it to be m to the power 0, L to the power 2, T to the power 0. So this is the dimension of area. Fine. Now let us find the dimension of force. We represent force by F. This is the scientific symbol. So when I wish to represent the dimension of F, this is how I have to express. So F will be equal to, F is mass times acceleration, m into a. So mass, dimension of mass is this one. Fine. Now you see, just we have represented few moments back, dimension of mass is m. So I have written this dimension of m, because force is equal to mass into acceleration. Acceleration will be what? L by t square. So it is L to the power 1 divided by t square, that means t to the power minus 2. Fine. And there is no component of mass, so m to the power 0. So now what happened? Just I need to add the powers of m, L and t. So here it is 1, here it is 0, so m to the power 1. L on this, here there is no L, so it is L to the power 1 and T to the power minus 2. So this is the dimension of force. So like that you can compute all the derived quantities dimension. But remember, dimension has to be written within third bracket. Fine. And this is how we calculate the dimension of any physical quantity. Now, dimensional equation. Dimensional equation, a very important topic. Fine. Dimensional equation. When a physical quantity is equated, that means equal to, equated with its dimension, the equation so forms is known as dimensional equation. When a physical quantity is equated with its dimension, the equation so forms, fine, is known as dimensional equation. Now you see here, this is what? Physical quantity is equated with its dimension. Now this is physical quantity F, force. And what is this equation? On this side we have dimension of physical quantity, namely force. So you see, when a physical quantity is equated with its dimension, on this side it represents the symbol. This is the symbol of force, F. But what is this equation? It indicates the dimensional formula of force F. This is equal to m to the power 1, L to the power 1, T to the power minus 2. So this equation itself is a dimensional equation. For example, say velocity. How we represent? Symbol of velocity is V. So the moment I write V within third bracket, it means it is representing the dimension of velocity. So this is equal to, I can write m to the power 0, L to the power 1, T to the power minus 1. So this becomes a dimensional equation. How I am writing this one? Because we know velocity is distance by time, length by time. So L to the power 1 and T to the power minus 1. So this is how we are writing the dimension of velocity. So this is called dimensional equation. On this side we will have the dimensional symbol of that physical quantity. This is what? This is dimensional symbol of the physical quantity. I can even say when the dimensional symbol of a physical quantity is equated with its dimension, then the equation it forms is called a dimensional equation. I can say when a physical quantity is equated with its dimension, or even I can say in a modified way, when the dimensional symbol of a physical quantity, when a physical quantity is equated with its dimension, I can definitely say, or in a modified way I can say, when the dimensional symbol of a physical quantity is equated with its dimension, then the resulted equation or the resulting equations so forms is called a dimensional equation. Fine. Now just let us try to know a new principle which is very, very important. Principle of homogeneity. Principle of homogeneity. This is very, very important. If you can understand this principle, everything related to dimension you can solve it within a moment. It is very simple. What it says is that the dimension of this principle says dimension of each and every term on either side of a physical relation or scientific equation or relation has to be same. Principle of homogeneity says dimension of each and every term on either side of a physical relation or on either side of a scientific relation or equation has to be same. Let me explain this term to you a little bit. Suppose I write an equation which all of you have come across in your class 10th standard, S is equal to ut plus half at square. This is what? This is a scientific equation or scientific relation or physical relation which we know from our class 10 knowledge, where S represents displacement, U represents initial velocity, T for time, F for acceleration, and this is a half. S is equal to ut plus half at square. This is a scientific equation or scientific relation or physical relation equation, that is equality sign. Now what principle of homogeneity says is that if this is a correct equation, then dimension of each and every term on either side of the equality sign has to be same. Dimension of each and every term on either side of a physical relation. Either side means this is one side, this is another side. On the left of equality side we have this term S. On the right of the equality sign we have these two terms. Which are the term? This is one term ut, another term half at square, another term S. On either side means on the left and right of the equality sign. So what this principle of homogeneity says is that dimension of each and every term on either side of a physical relation has to be same. That means if S is equal to ut plus half at square has to be correct, if it's a correct equation, then dimension of S This is a term. This is a term. This is another term. ut as a whole, it's a term. Half it is square as a whole, it's a term. This is a term. This is another term. This is another term. These two terms are appearing on the right of the equality side. This term is appearing on the left of the equality side or sign. So principle of homogeneity says that if it is a correct equation, the dimension of each and every term on either side of the equality sign has to be same. That means if it is a correct equation, the dimension of this term s has to be equal to dimension of the term ut has to be equal to the term dimension of the term half it is square. Now let us check whether it's true or not. Now the dimension of s. So this is dimension of s. This will be what? S is nothing but displacement. So we can easily write it is L to the power 1 T to the power 0, because in order to measure the displacement we need not to worry about the mass and time. It only depends on the fundamental quantity length. So this is the dimensional formula of S. Now what is the dimensional formula of ut? There are two quantities, u and t. T is a fundamental one, but u is the initial velocity is a derived quantity. So dimension of ut will be comprising of dimension of velocity as well as dimension of time. What is the dimension of velocity? It is L t to the power minus 1. And what is the dimension of time? It is 2 to the power 1. So combining these two terms, I can write it is m to the power 0 because there is no m. L to the power 1 and t to the power 0. So this is the dimension of ut. What is the dimension of half it is square? As we know, half is a number, so it is dimensionless. It has got no dimension. Forget about it. What is the dimension of a? It is m to the power 0, L to the power 1, t to the power minus 2, and there is again a t square. So what is the dimension? T to the power 2. So combining these two terms, we can write m to the power 0, L to the power 1, t to the power 0. Now you see the beauty. The dimension of the term s, this is equal to m0, L1, t0. Dimension of the term ut, again m0, L1, t0. Dimension of the term half at square, again m0, L1, t0. That means what we find? The dimension of each and every term on either side of the equality sign is same. And therefore we can conclude that it is a correct scientific equation. So this is what is being said by the principle of homogeneity. It says that if we have a correct scientific equation, then each and every term on either side of the equality sign must have the same dimension. So this is what is meant by principle of homogeneity. Now here you have seen one of the advantage of knowing the dimension of any physical quantity. So I can say dimensional formula helps us to check the correctness of a physical equation. If we want to check the correctness of a physical equation, this is the way. The dimensional formula can help us really in detecting the correctness of a physical equation. Whether a given equation is correct or not, we can easily assess, we can easily know if we know the dimensional calculation. So if we just calculate the dimension of each and every term, and we find that yes, dimension of all the terms are equal, then you can conclude that the equation is a correct one. So conclusively we can say that dimensional formula helps to check the correctness of a physical equation. Because we have seen, if we consider the equation s is equal to ut plus half it square, then just if we equate the dimension of all the terms, if we calculate the dimension of all the terms and if we find that all the terms are having equal dimension, then you can easily predict that it's a correct equation. So this is one of the very advantage of knowing the dimensional formula. Or I can say this is the importance of dimensional analysis. Now number second, let us see again what is again the advantage of dimensional analysis. Let us see one more case. Dimensional formula helps us to find the conversion factor of units of same physical quantity. In different system of units. So first we have seen dimensional formula helps to check the correctness of a physical equation. I hope you have understood. Second, let us see how it can help us to find the conversion factor of units of same physical quantity. So there will be one physical quantity which will have different units in different system. And let us see the conversion factor. For example, say we want to find the relation between Newton and dyne. Suppose I don't know what is the conversion factor. That means what is the relation between Newton and dyne. I would like to find what is the figure here. I don't know. Say for example I consider that I don't know the conversion factor. So arbitrarily I am just considering 1 Newton is equal to x dyne. Just only thing is known to me that Newton is nothing but the unit of force in SI system of unit, and dyne is the unit of force in CGS system of unit. Only this information is known to us. That you just see here we are focusing on unit of same physical quantity. On this side also this is the unit of force, this is also the unit of force. It is not, we are not concerned with the different physical quantity. We are considering a single physical quantity, but it's different units. That means units in different systems. On this side we have SI system, on this side we have CGS system. We would like to find out the relation between them. So say I consider 1 Newton is equal to x dyne. Only the information is known to me that Newton is nothing but the SI unit of force and dyne is the CGS unit of force. Now say in SI system L1 M1 T1 represents dimension of fundamental units. Say I consider fundamental units. That means say on SI system I represent length by L1, mass by M1, time by T1. Similarly, say on CGS system, so the respective fundamental units be represented by L2, M2 and T2. Remember, this is not power, this is just a representation. In order to represent all the things in CGS system, we are representing length by L2, M by M2, T by T2. On SI system, we are representing the same quantities by L1, M1, T1 respectively. This has nothing to do with the values of length, time and mass. So now if I consider that this is a correct equation, because I want to find the relation, so this has to be correct of course, then what is the dimension of, this is the unit of force, so the dimension of force we have just calculated, it is ml t to the power minus 2. So what will be the dimension of force if I use SI system of unit? Generally it is L m t to the power minus 2. This is generally the dimensional formula of force. Now in SI system, when I am representing the force whose unit is Newton, in that case the respective fundamental units are represented by not by LMT but by L1, M1, T1. This is just a representation. So I can write it. Now this is equal to what? This is x. This is a number because conversion factor is merely a number. A number has got no dimension. So I need not to consider the dimension of x. X remains x. Again, what is the dimension of force in CGS system? Dimension will remain the same. L1, M1, T to the power minus 2. But on CGS system, we represent length by L2, M by M2, T by T2. So now I can write, or x equals this divided by this one. So I can write L M T 1 1 1 minus 2 1 1 divided by L2 m2 this one. So this is equal to L1 by L2. Here power of L is 1, power of L is 1. So L1 by L2 whole to the power 1. Similarly M1 by M2 whole to the power 1. T1 by T2 whole to the power minus 2. Now L1 by L2. L1 is in SI system. L2 is in CGS system. What is the unit of length in SI system? It is meter. What is the unit of length in CGS system? It is centimeter. Fine. So I can say it is meter by centimeter whole to the power 1. M1 by M2. This is in kilogram, because in SI system unit of mass is kg and in CGS system unit is gram. So kg by gram into 1. And the unit of time in both SI and CGS system is second. So it is second by second whole to the power minus 2. So this becomes what? Meter by centimeter. So it is 10 to the power 2. Kilogram by gram. It is 10 to the power 3. And this is second by second is 1. So 1 to the power minus 2 is again 1. So what we get? 10 to the power 5. So what do we find the value of x to be 10 to the power 5? So I can write that 1 Newton equals 10 to the power 5 dyne. So dimensional formula, you see how dimensional formula helps us to find the correct conversion factor of units of same physical quantity. Here the quantity was force. So dimensional formula helps us to find the correct conversion factor of units of same physical quantity in different system of units. So this is one of the biggest advantage of dimensional analysis. Now let us see the last but not the least, one more advantage of knowing the dimensional analysis or doing the dimensional analysis. Dimensional formula helps to establish also helps to establish relationship between physical quantities. Let us see how. Suppose I tell you the time period of a pendulum, let it be t, represented by t, depends on time. I am telling time period of a pendulum, say, depends on length of the pendulum L and acceleration due to gravity G. Just I am telling that suppose I have a pendulum, you know, this is a simple pendulum and this is the length. So time period means the time it takes to complete one oscillation. This is what is called time period. Just I am giving you the information that the time period of this pendulum depends on which factor? Depends on length and the acceleration due to gravity. And you have to give me the exact relationship, actual formula of time period connecting with L and G. So just I have given you the idea that T depends on L. That means T is proportional to L. But I don't know which power of L. It may be L to the power 1. It may be L square. It may be 1 by L. It may be 1 by L square. It may be E to the power L. It can be anything. I don't know. So arbitrarily I am considering that the power be X. So I have to find out what is the value of X. Because I don't know. It is just said that time period depends on length. But by which factor I don't know. Whether it depends on L or L square or L cube or L to the power 4 or L to the power 5 or root L, I don't know. So arbitrarily I have considered that the time period depends on L by a factor L to the power X. Similarly, I don't know what is the power of G. Means whether it is root g or g square or g cube or 1 by g, I don't know. So I have considered that the power on which the time period depends with g, it is d to the power y. So combining these two proportionality sign, I can easily write an equation t equal to some constant L to the power x, g to the power y. Now you just give your attention here. I have already given you the information that time period depends on L and G. The moment I have given you this information, you have to consider that this is a correct statement, because you are being supplied with the instruction that time period t depends on L and G. So you have to believe that it's a correct information. So you have to proceed with this correct information. So if I consider that this is a correct information, then I proceed up to here. T is equal to k L to the power x, g to the power y, where this k is a constant. It is not a physical quantity. So k will be dimensionless quantity. So now, considering that this is a correct equation as per the supplied condition, let us apply the principle of homogeneity. What it says, if it's a correct equation, dimension of each and every term on either side of the equality sign has to be same. Now what is the dimension of time period? Time period, that means time taken during one complete oscillation. So this is basically a time. So what will be the dimension of time? So I can write dimension of time, this is equal to k, it is not dimensionless, dimension of L to the power x, dimension of g to the power y, if it's a correct equation. Now what is the dimension of t? It is nothing but m to the power 0, L to the power 0, t to the power 1. So this is equal to k. Dimension of length is m to the power 0, L to the power 1, t to the power 0, and whole to the power x is there. Similarly, what is the dimension of g? Acceleration due to gravity. That means basically it is an acceleration. So it is m to the power 0, L to the power 1, t to the power minus 2, whole to the power y. So this becomes k m to the power 0, L to the power x plus y, t to the power minus twice y. Now if this is the correct equation, then dimension of this term L to the power x, g to the power y has to be equal to dimension of t. That means m to the power 0, L to the power 0, t to the power 1 has to be equal to m to the power 0, L to the power x plus y, t to the power minus 1. So comparing the coefficients of L and t on both sides, what we got? This x plus y has to be equal to 0, because L to the power 0 has to be equal to L to the power x plus y. That means x plus y has to be equal to 0. Similarly, t to the power 1 equals to the power minus twice y. That means minus twice y equals 1, or y equals minus half. If y equals minus half, x will be, x plus y is 0. If y becomes minus half, so x has to be equal to half. So we already obtained the values of x and y. X is plus half, y is minus half. So I can write t is equal to proportionally constant L to the power half, g to the power minus half. That means it is k root L by g. So this is the equation. So you see how nicely dimensional formula helps us to find even the relationship between various physical quantities. I have given you the information only that t depends on L and G. Nothing has been said to you more than this. But with the help of dimensional analysis, so nicely we can find the expression of time period connecting L and G. So this is one more advantage of dimensional analysis. So in the next class we shall be strictly doing lots of numerical problems related to dimensional analysis. So I stop my today's class here. Thank you.